Okay, in this example, we're trying to find the minimum head rise across a pump to provide a flow rate of almost 19 liters per minute, or 5 gallons per minute of water to this tank. So basically what we're doing is we're trying to pump water out of a lake through this pipeline and into a tank at a cottage. And we're told some information about the situation. We're told some elevations here. We're also told that we're dealing with a smooth plastic pipe, 2 inches in diameter, and there's a total of almost 29 meters of it. And then a number of pipe components, like a reentrant inlet right here. We're told we have 10 90-degree flanged elbows, some unions, 8 unions. Unions are used to connect straight sections of pipe together. A fully open globe valve and 4 fully open gate valves. So we want to know what's the minimum head rise we need to have across a pump to give us the desired flow rate, and what power should be supplied to the pump, assuming a pump efficiency of 65%. Okay, so I want you to ask yourself how we're going to approach this problem. What tool should we use to analyze this system? Okay, so it's the extended Bernoulli equation. So let's write that out. So we're going to use the extended Bernoulli equation. So we'll write out the full equation. It goes between 2 points, point 1 and point 2. And so the 3 dots here just is the same as this. I just didn't want to write it out. So we need to identify our points 1 and 2 where we're going to apply the extended Bernoulli equation. So think about for a moment where we're going to put those points 1 and 2. Now keep in mind that what we're trying to do is find the head rise across the pump. So you'd want the pump in between those 2 points. And then usually when you choose the points 1 and 2, you want to put them at locations where you know a lot of information. So think for a moment where you would apply those 2 points. Okay, so point 1 I would place right here on the free surface, because we know the elevation of that surface, we know the pressure there, we know the velocity is approximately 0. And then there's some streamline that goes through the pipeline, through the pump, and then I would put point 2 right there, right at the outlet of the pipe, because there again I know the elevation, I know the pressure, I don't know the velocity, but that's, I don't know it explicitly here, but we can actually calculate it. So those are the 2 points I'm going to choose. Now we'll write out information about the 2 points. So what's the pressure at point 1? Well, since it's a free surface right here, so it's on the free surface of the lake, the pressure there is going to be atmospheric pressure. What about at point 2? Right here. Well, there the pipe is discharging into the atmosphere, so it would be a free jet. So the pressure there is also atmospheric pressure. What about V1? So the velocity of the lake, the average velocity of the lake. Well, since it's a big lake, the velocity there is nearly 0. And it's a very good approximation to say it's 0 because the lake is so big. It's moving down slightly because we're drawing water from it, but it's insignificant. So it's very reasonable to say that the velocity is 0. How about the velocity at 2? Well, there we can actually calculate the velocity. We're told what the flow rate is, so let me highlight that. So we're told the volumetric flow rate is almost 19 liters per minute. And then we also know the diameter of the pipe, so we should be able to calculate the velocity right at the outlet there. So this would be the volumetric flow rate divided by the cross-sectional area of the pipe. And the cross-sectional area of the pipe would just be pi over 4 times the pipe diameter squared, and we could plug those values in. I don't, let me just write them down. We'd have to do some unit conversions, and I did not actually do those unit conversions here. But I'll just write the numbers so you know which numbers to put in. So this is the volumetric flow rate, Q, that's given here. And then here's the pipe diameter right there. So that's 5.08 centimeters. So you'd have to do a unit conversion to make that work out. So unfortunately, I don't, like I said, I don't know what the value of V2 is. I didn't actually compute this out. So I'll just put some equal to dot, 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 and you'd probably put it in meters per second. Okay, now we have Z2 and Z1. Well, Z1, you can see we have, let's put that as our reference point. So we can put Z there. So Z1 would be equal to 0, and Z2 would be this height right here. So you can see that that would then be 15.24 meters. Okay, so far so good. Let me now go to the head loss term. So what two types of head loss do we account for? So what are the two big categories of head losses? We have major head losses and minor head losses. So let me write those down. So we have a major head loss and we have minor head losses. So how would we find the major head loss? Okay, so for that, the major loss coefficient is the friction factor times the length of the pipe divided by the diameter. And then we multiply it by the velocity head where that loss occurs. So before we evaluate the friction factor in L over D, let's just focus on the velocity where that loss occurs. So the major head loss would be in this pipe. So what's the velocity inside the pipe? It would be the same as V2, right? Because that's the velocity in the pipe. The pipe has the same diameter everywhere, so it's going to have that same velocity all throughout the pipe. The L we're given, right? We're told that we have 28 meters of that pipe, or I'm sorry, it's almost 29 meters. So the L is going to be 28.96 meters. The diameter, we just said moments ago, was 0.0508 meters. V2, presumably we have calculated that already up here. Now we need to find the friction factor. So how would we find the friction factor? Okay, so in general, the friction factor is a function of the Reynolds number and the relative roughness of the pipe. Let's first focus on the Reynolds number. So the Reynolds number, based on the pipe diameter, will be the velocity in the pipe, so that's V bar 2, times the pipe diameter divided by the kinematic viscosity of water. So we can look up the kinematic viscosity of water. So we can presumably find that. I think that's 1 times 10 to the minus 6 square meters per second. So let me just write that here. 1 times 10 to the minus 6 square meters per second. Then the velocity V2 we had calculated earlier here. And the pipe diameter we know is the 0.0508 meters. When you calculate that out, and I actually did do that calculation, it comes out to be about 7,900. So does that mean that the flow is laminar or turbulent in the pipe? Well, since it's greater than 2,300, we know that the pipe flow must be turbulent. Since it's turbulent, what would the kinetic energy correction factor be up here? We forgot to talk about that one. So the alpha 2, by the way, we don't need to worry about alpha 1 over here because V1 is equal to 0, so it doesn't matter what alpha 1 is. But for alpha 2, what's that going to be? So that should be equal to about 1. When you have a turbulent flow, recall that the kinetic energy correction factor is about equal to 1 because that turbulent velocity profile looks pretty close to an average velocity profile. So the kinetic energies are about the same so that you don't have to do a correction. Okay, so we have the Reynolds number. What about the relative roughness? Well, the relative roughness in this case is actually 0 because we're dealing with a smooth plastic pipe. So the relative roughness is 0. It doesn't mean the pipe is frictionless. It just means that the relative roughness is 0. So now that we know the Reynolds number, and we know that we're dealing with a smooth pipe, we can find that friction factor by going to the Moody plot. So let me skip over to a Moody plot. So here's a Moody plot. And again, we said that we're dealing with smooth plastic pipe. So that means we're going to be following this smooth pipe curve here. This one says smooth pipe. So we're going to be following that line. We said that Reynolds number was about 7,900. So that puts us right about here, pretty close to 8,000. So we'll run up vertically there. I'll do my best to draw a straight line. We intersect with that smooth line, smooth pipeline, and then we come over to there. And so when I did this a little more carefully before, I came out to about 0.033 for my friction factor. It's an approximate value, okay? So now we know our friction factor. Let's go back to our problem. So from the Moody plot, we find that the friction factor is about equal to 0.033. Okay, so now we know that value. So now we have everything we need to find the major head loss. Now let's do the minor head loss. So that one, I'm just going to write it here as the sum of all the minor loss coefficients times the velocity heads where those minor losses occur. So this term, this minor loss term, will account for the reentrant inlet, the elbow, the union, and the globe and gate valves. So let me just jot that down here where we have a little more space. So the minor head loss term, we're going to have one reentrant inlet. We're going to have, oh, and by the way, before I continue that, the velocity heads where those losses occur, since in this entire pipe we have the same velocity because it's all the same diameter, it's going to be the same velocity head everywhere. And that velocity head will be based on V2 because that's the velocity inside the pipe everywhere. Okay, so we have one reentrant inlet, and then we have 10 elbows. We have 8 unions. We have one globe valve. And then we have 4 gate valves. And all of those are multiplied by the velocity head based on the velocity V2. So how would we then find these minor loss coefficients? Okay, so those we find from a minor loss coefficient table. So I have a table of minor losses. Let me see if I can find it. Here we are. So here's our table of minor loss coefficients. So you can see, for example, a regular 90-degree flanged elbow has a minor loss coefficient of 0.3. The reentrant inlet has a minor loss coefficient of 0.8. The threaded union has a minor loss coefficient of 0.06, and so on. So we can write down all of these various minor loss coefficients. So I think we had a fully open globe valve, and I think we had a fully open gate valve as well. I don't really recall whether they were fully open or not, but this is how we find our different minor loss coefficients. So let's go back to the problem. One other thing I'll just mention about the minor losses, if you go back up here, there is no there is no exit minor loss here at the exit. When the flow comes out of this pipe, it's not being mixed at this point with surrounding fluid. When it comes out of here, there is no loss in the kinetic energy of the fluid as it leaves. So there is no exit loss. If we had put that pipe all the way submerged in the tank with if the tank was filled, to that level, and then we submerge the pipe down into the bottom here, then it would mix around. And if we chose our 0.2 at the free surface, at the free surface of the tank, then we would have an exit loss of 1 because we would lose all the kinetic energy in the flow as it came out of the pipe and went to the free surface, because the velocity on the free surface is equal to 0. So all that kinetic energy coming out of the pipe would have been dissipated away. But because we chose our 0.2 up here, when the fluid velocity comes out of the pipe, it hasn't lost any kinetic energy. So there is no exit loss. Okay. So getting back to this, we can look up all of these various values and plug them in. We already know V2 because presumably we found it up here, so we can calculate the minor losses. Okay, so that takes care of this term. And then what about this last term? Let me just zoom out here. What about HS? Well, that's what we're trying to solve for. So that's, we're trying to find the minimum head rise across the pump to provide this given volumetric flow rate. So we're trying to find what this head rise is across the pump. Remember, this is the shaft head term. It's the energy or head rise we put into the flow because of a rotating shaft, like a rotating shaft you'd have in this pump. So that's what we're trying to solve for. So if we take all of these values that we've calculated and plug them in and solve for HS, let me go ahead and do that and then tell you what the result comes out to be. That'll come out to be 15.28 meters. So that's the head rise we need to put into the fluid in order to make it flow at the given flow rate. Now, just a couple of items I want to discuss here. First of all, you'll see that the head rise we need from the pump that goes into the fluid is really not that different from the elevation head. Right? It's just a little bit larger than the elevation head. What that means is that most of the head rise we need from the pump just is overcoming the elevation difference. The extra little 0.04 meters here is because of the major and minor losses. They're just very small. The flow rate through the system, if I did all my numbers correctly, just doesn't result in very large major or minor losses. They're just small in comparison to the elevation head difference. Now, if we had a higher flow rate, then those major and minor losses would be more significant. And then this value would be bigger because we'd have not only the elevation head we have to overcome, but we would also have larger major and minor losses. So by noticing this, it just means that we're really just mostly overcoming the elevation differences. The second thing I wanted to mention on this is the head that we have to put into the fluid. Okay, now because the pump's not 100% efficient, we're going to have to put some additional energy into the pump, and some of it is just overcoming the inefficiencies in the pump, but then we ultimately need to get the 15.28 meters into the fluid. So let's calculate the power that needs to go into the fluid. So how would we calculate that? If we know the head rise that needs to go into the fluid, how would we get the power that needs to go into the fluid? Well, that can be found from relating the shaft head term to the power, shaft power. It's just the shaft power divided by the mass flow rate divided by the gravitational acceleration, or if you like it in terms of volumetric flow rate, it'll just be the density times the volumetric flow rate times g. And so we could rearrange that equation to solve for the shaft power. This is the power that needs to go into the fluid. So we know all of these values on this side, and we can calculate the power. When we do that, that comes out to be, let's see, 47.3 watts, if I've done all my calculations correctly. So that's the power that goes into the fluid. It's the power that needs to go into the fluid in order for the fluid to flow at that flow rate. Now we're told that the pump is only 65% efficient. So if this is the power that needs to go into the fluid, what power needs to go into the pump? Well, to find that, so I'll write the power into the pump. It'll be the power that we need to put into the fluid divided by the efficiency of the pump. Because we have to put a little extra power into the pump because it's not 100% efficient. So if we use our 0.65 here because it's 65% efficient, and then the power that goes into the fluid we said was 47.3 watts, then you'll find that the power that we have to put into the pump is 72.7 watts. In English units, that's about 0.1 horsepower. It's not that much. So that's the power we need to put into the pump because it's not 100% efficient. If it was 100% efficient, all the power we put into the pump would get into the fluid, but we know that there's some losses inside the pump. So we have to put a little extra power into the pump so that we can get the right amount into the fluid. Okay, so hopefully that example all makes sense to you. It's really an application of the extended Bernoulli equation, making sure you use good points in the Bernoulli equation, extended Bernoulli equation. Then you evaluate what all those parameters are at those different locations. We had to calculate a major and minor losses, where the friction factor in the major loss, we had to use the Moody Plot with the calculated Reynolds number, and knowing that we're using a smooth pipe to get the friction factor. The minor loss is due to a bunch of different components that we used a table to look up those values. We could then find the power that goes into the fluid by relating the head that goes into the fluid and the power using that relation. And then we could find the power that goes into the pump because we know the power that needs to get into the fluid, and we divide it through by the pump efficiency. Since we know the pump, we have to put extra power into the pump in order to get the right amount into the fluid. Okay, we'll go ahead and end the example there.